Hi everyone. In this video we're going to work through a bunch of, random, jumbled up example problems that have to do with limits. So our first example says, use a calculator to estimate the given limit numerically. And our limit is asking us, what's the limit as x approaches 1 of natural log x divided by x minus 1? And so if I actually just plug in x equals 1, we can see what happens. That would give me natural log of 1 over 1 minus 1. And I know that natural log of 1 is 0 because any logarithmic function, when you use 1 as an input, any logarithmic function will give you 0 as an output. And of course 1 minus 1 is 0, but this is not a real number, and so we would say that the function is undefined here. So I can't just plug in x equals 1 this time. I actually need to maybe take the left-sided limit and the right-sided limit and see if they reach the same thing for this two-sided limit. And to do this, I'm going to use Microsoft Excel. It says to use a calculator, but on this computer, for some reason, I don't have a built-in calculator, so here we go. I'm going to start with the left-sided limit. And I'll make a column for my input values and for my output values, which should be natural log of x divided by x minus 1. And I'm trying to approach x from the left side. I'm trying to approach x equals 1 from the left side for my left-sided limit. And so I'll start maybe from half. Seems like a good number. And then maybe also 0.75. Maybe like 0.9, 0.99, 0.999. And with each new row, I'm getting closer and closer to 1, approaching it from the left side. It doesn't really matter too much what numbers you choose here, but the idea is that we're just approaching it from the left side. And we can even, just plug in 1 to see what happens here. And if you don't have much practice with Microsoft Excel, I really highly recommend it, especially with this being a calculus for business class. Because if you work any sort of business job, Microsoft Excel skills are very highly valuable. So what we're going to do here in this cell, so I'm going to type in equals ln, and the ln function is going to return the natural logarithm, open parentheses. And then instead of x, I'm going to actually just click on the value 0.5. I'm going to click on that cell, and it will highlight it for me. And then I do close parentheses divided by open parentheses. I'm going to click on the cell again to get my x value, and do -1 close parentheses. When I've typed my little Excel formula here, just like this, I'm going to hit enter, and it's going to return a value, which is this expression if I were to evaluate it at x equals 0.5. And with Excel, it's really powerful because you can create a full table of values really easily. And so what I'm going to do is click on the cell that has my little cell formula and the value 1.38. And in the bottom right corner, I'll click and I'll drag it down to complete my whole table. And so what we can see now is that, first of all, if I click on any one of these cells, it changes the reference so that on this row, it's not referencing the 0.5 anymore, but it's actually referencing the 0.99999. And what I want you to see is that as we approach 1 from the left side, these values are going from 1.38 to 1.15 to 1.05, and so on, and they're getting closer and closer just to the number 1. When we actually reach x equals 1, remember that my function isn't defined here. So Excel actually can't help you if I just plug in x equals 1, but by looking at this sequence of times we've evaluated the function, we can see that these numbers are actually getting closer and closer to that 1. And Excel is also really good for visualizing things. If you highlight a table of values, and you go up to the Insert tab, and then right here where it says Scatter Plot, Insert Scatter, you can choose a scatter plot. And again, this horizontal line represents 1 here. And so as we do more and more iterations, going from 0.5 and getting closer to 1 in the input, our output also approaches 1. So we can see that there. Okay, but this is mostly what we were asked to do here. For example 1, use a calculator to estimate the given limit numerically. What you would do if you had a calculator in your hand is you would plug in values for x, starting from the left of x and getting closer and closer to 1. And actually, one thing that I've neglected so far, but it's pretty easy to show, I actually just showed you the left-sided limit, but we can also do the right-sided limit just to verify that this two-sided limit really exists. So let's just make sure that the right-sided limit gives us the same thing. I'll scooch over a little bit, and then I'll do right-sided limit. And I'm trying to approach x equals 1, this time from the right side. So I might do like 2, 2.1, 2.01, 2.001, 2.000. Oh, excuse me. I should say 1.1, 1.01, 1.001, because I'm actually trying to approach the number 1 coming in from the right side. So something like this. And these are the values that I'm going to be using for my input. And for the output of the function, I actually want the same thing. And so as we get closer and closer to the number 1 coming in from the right side, you can see that these values go from 0.69 to 0.95 to 0.995, 0.9995, and so on. They're actually getting closer and closer to 1 as well. So my right side limit is also 1 here. Example 2 says, suppose the following statements are true. And so my first statement says that the limit as x approaches 4 of a function f of x is equal to 5. My second statement is saying that the limit as x approaches 4 of the function g of x is 2. And it wants us to use limit properties to find the given limit. And this limit looks pretty hairy, but it's asking for the limit as x approaches 4 of 5 times g of x cubed minus 4 divided by 1 minus f of x. And what I see here is I see that this limit is actually a limit of a quotient here. So I have something in the numerator divided by something in the denominator. And I want to remind you of the previous video, and maybe a moment. Let me pull up that. Okay, here we go. The limit rules from the previous video. We had this quotient rule, which says as long as the limit of your denominator is not equal to 0, then you can actually break apart a limit of a quotient into a quotient of two limits. So hopefully everyone sees this, and you can pause the video if you need a moment to sort of soak that in. But what this means for us in this example is I can break this into the limit as x approaches 4 of just the numerator, 5 times g of x cubed minus 4, divided by the limit as x approaches 4 of my denominator, which is 1 minus f of x. And I can do this because I think that the limit as x approaches 4 of 1 minus f of x is not going to be 0. And if it is, then I guess we'll find out here in a moment. So that's my first step. In the numerator here, I see that that limit is actually a limit of two things that are subtracting each other, right? So I have on the left side 5 times g of x cubed, and on the right side minus 4. So if I go back to my limit rules, we have a limit rule about this as well. And so this right here is telling me that the limit of a difference is equal to a difference of limits. In other words, if I see a limit that's just two things, with a minus sign between, I can actually break that up into the difference of two limits here. So let's apply that idea. Going back here to the numerator, that means that I'm taking the limit as x approaches 4 of 5 times g of x cubed minus the limit as x approaches 4 of 4. And in the denominator, I can use exactly the same idea, because in the denominator I also have a difference inside of that limit, so I can break that into two limits and take the difference of those limits. So the limit of 1 as x approaches 4 minus the limit of f of x as x approaches 4. Okay, so that's my second step. And we can do some simplifying here, because the limit of the number 1 as x approaches 4, well, actually, the number 1 here, that does not depend on x. And so the limit as x approaches 4 of the number 1 is just the number 1. There's no dependence on x here. And then the same thing over here, the limit of the number 4 as x approaches 4, well, the number 4 doesn't change. It doesn't really care about what x is approaching. And so the number 4 is going to be the number 4. Right? So a little bit of simplifying here. Then, in the numerator, I still have this limit as x approaches 4 of 5 times g of x cubed, but there's a limit rule for products, which is to say that if I have, 5 times something, like h of x function, I'm taking the limit, this is just 5 on the outside of the limit, times the limit of h of x, right? This is what this is telling me. If there's a constant multiplier inside your limit, you can just pull it outside of the limit. And so this is what I'm going to do here. I'll rewrite that as 5 times the limit as x approaches 4 of g of x cubed. And then I'm going to subtract 4 from the numerator again, and then I have 1 minus the limit as x approaches 4 of f of x. But actually, I was told up here that the limit of f of x as x approaches 4 is the number 5. So that was one of my givens in this problem. And so I can replace this with the number 5. So I have 1 minus 5 in my denominator now. Okay. In the numerator, when I have 5 times the limit as x approaches 4 of g of x cubed, I can actually write this as 5 times the limit as x approaches 4 of g of x, all of that cubed. I'm going to cube the limit instead of cubing g of x inside the limit. So in one moment, oh, by the way, 1 minus 5 in the denominator. 1 minus 5 is just 4. And why could I do that? Why could I bring that cube outside of the limit? Well, actually, that's also one of our limit rules. I called it the power rule for a limit. So when I had the 4th power inside the limit, I could actually just bring that outside of the limit, and it was totally fine. Now, recognize that I have limit as x approaches 4 of g of x, but that is the number 2 by the problem definition. And so replacing that with the number 2, I have 5 times 2 cubed minus 4 over 4. 2 cubed would be 2 times 2 times 2, so that would be 8. So I have 5 times 8 minus 4 over 4. 5 times 8 is 40. And so 40 divided by 4 is 10. 4 divided by 4 is 1. And so the answer to this example 2 is 9. And that was kind of a long example, but I wanted to demonstrate, a way that you might be asked to apply the limit rules that we learned in a previous video, right? So why did we even bother learning these? Well, some of your problems are going to require you to know this. I'm going to actually erase this over here on the right side so I have more room to work. And we're ready to work on example 3. So example 3 says, graph the function h of x. And this is an important example because h of x is what we call a piecewise function. And I call it a piecewise function because the function h of x comes to us in 3 pieces. Basically, if I were to plot this on an xy plane, so this is my x-axis, and this axis represents the output of that function. Whenever x is less than negative 2, it's given by the rule 3 minus x. 3 minus x. And that means actually these values are going to be pretty large. But, oof, I'm going to have a difficult time drawing this. So maybe I need to erase even more. It's 3 minus x, and so that means my y-intercept is 3, because when x is 0, it's going to be 3. And then it's going to have a slope of negative 1, because of that negative x. So for example, whenever x is negative 3, this value here should be like positive 6. And so I've got this descending sloping line, but it only goes up to x less than negative 2. And this is that piece of the function, right? That first piece that applies when x is less than negative 2. And then for my second piece of the function, if x is greater than or equal to negative 2, but less than 2, so here's 2, it's going to follow the rule x plus 2. And so in this case, my y-intercept is 2, and I have a increasing slope to my line this time for x plus 2. And so it's going to look like this for that middle piece of the function. And then the last piece of the function here, it's just going to be equal to 3 if x is greater than or equal to 2, right? So here, when x is 2 or greater, the function output is just the number 3. And I admit I'm not the best at drawing, and so maybe we can put this into Desmos and we can see it done a little bit more professionally, right? So let's try this. My first branch of my function is going to be 3 minus x, but only if x is less than negative 2. And my second branch, or piece of my function, I should say, is x plus 2, but only if x is between negative 2 and 2. And then finally the third piece of my function, third piece of my piecewise function, is just the value 3 if x is greater than or equal to 2. And so this is a piecewise function because it comes in 3 different pieces, right? The first, second, and third pieces are red, blue, and green here on Desmos, as you can see over here. And so what we want to do is we want to use this to evaluate the following limits. So going back to my example, I want to find the limit as x approaches negative 2 of this function. So as x is approaching negative 2, which is right here, what's happening? Well, my right-sided limit is going to be coming in from the right, approaching negative 2. That sort of makes it look like the value of the function is approaching 0. So my right-sided limit here, the limit as x approaches negative 2 from the right side of my function, that is approaching the value 0. The left-sided limit, as x approaches negative 2 from the left side, is going to be actually a lot greater than that, right? So it'll be following the rule of the first piece of the function, which would be 3 minus negative 2, or it would be 5, right? So as I come in from the left side here, it's approaching the value 5. That might be easier to see if I bring up Desmos again. Yeah, as I'm coming in from the left here, I'm approaching this value here at negative 2 comma 5. And so since the right side and left side limits don't agree, since 0 is not equal to 5, that means this two-sided limit that it's asking for does not exist. And it also asks, what about the limit of this function as x is approaching positive 2? Well, my right-sided limit is dealing with this third branch, so I'm coming in from the right, and it's just staying a constant 3. So as x approaches 2 from the right side, my limit's going to be 3. And for my left-sided limit, as x approaches 2 from the left side, it's talking about this middle branch, and as I approach 2 from the left side, this middle branch is approaching the value 4. And so again, this two-sided limit that it's asking for does not exist because my two one-sided limits, the right side and the left side, don't agree. Now, this was a piecewise function that had two discontinuities. You know, it had discontinuities when you went from the first piece to the second piece, and had a discontinuity when you went from the second piece to the third piece. But you actually can have piecewise functions that don't have discontinuities, right? Like I could actually fix this one really quick. By making that middle piece x plus 1 instead of x plus 2, now there's no discontinuity as I'm going from the second piece to the third piece, right? So the second piece and the third piece meet up where x is equal to 2. They both have a limit, a one-sided limit that approaches 3. And again, on my left branch, or my first piece of my piecewise function, I could actually fix this a bit if I allow this to be -3 instead of +3. And now I have a piecewise function that's defined in 3 pieces, but it's actually a perfectly continuous function. So you can have a continuous piecewise function, or you could have a piecewise function that is not continuous at the junctions between the two pieces. Okay. Example 4 here is asking for the limit as x approaches 2 of x cubed minus 3x squared plus x minus 5. And hopefully you guys recognize this as being a polynomial. And when we were first learning about limits, we learned that the limit as x approaches anything for a polynomial is just the polynomial evaluated at that point. And the reason for this is because polynomials are always continuous. Let me write that out. Polynomials are always continuous. And that means instead of having to, mess around with graphing this or doing any sort of fancy tricks, I can just replace x with 2 and write 2 cubed minus 3 times 2 squared plus 2 minus 5. Now 2 cubed is 8. 2 squared is just 2 times 2 is 4, plus 2 minus 5. So 3 times 4 is 12, and 8 minus 12 would be -4. -4 plus 2 is -2, and then -2 minus 5 is going to give me -7. So this was as easy as just evaluating that polynomial at the point.